Hello everyone, my name is Amjad. I am a research associate at the Center for Parallel Computing, which is a research group in the University of Westminster, UK. Today I am here to present MiCADO system, which is a software tool for dynamic management of Docker containers in multi-cloud and edge environment. In this talk, I will mainly talk about MiCADO system, which is an application level cloud orchestration solution. This tool was developed within the scope of a European research project called Ullah. MiCADO is available as a managed service as well as an open source community version as well. Further in this talk, I will also present two extensions of MiCADO, one with the name JQuery, where we extended MiCADO in order to support the execution of container-based batch application in cloud environment. And the second extension is called MiCADO H, where we extend the capabilities of MiCADO system such that the orchestration of application in the extended cloud to edge ecosystem can also be managed. Now, in order to understand what MiCADO is and how MiCADO works, let's try to consider a scenario. For example, there is an application owner or developers which has an application. This application consists of a set of microservices. These microservices are expected to run in Docker containers, and these Docker containers can either reside in a private repository or in a Docker hub. Now, in order for these applications to run and manage within the cloud environment, so this application owners or developer has to choose which cloud providers which cloud environment they would like these applications to be deployed and executed in. So the developer has to make a number of choices in terms of the cloud providers. Once a cloud provider has been chosen, then the developer has to select what kind of VMs, virtual machines they would like to use for the deployment of these resources. And once these virtual machines are being selected by the developers, then they would like to kind of identify which service of the applications needs to run on which particular virtual machine. So they have to perform a service to virtual machine mapping, and once such mapping has been performed, so maybe the developers and the application owners would like to associate and attach some custom policies which needs to be run and managed, which control the executions of this application. And these policies can be like monitoring in order to measure the different various aspects of the applications and resources, or scaling policies which can dynamically do the reconfigurations of the resources required for the applications, and maybe some security application specific security policies. Now, in order to do all these things and how this can be managed, MiCADO facilitate such cloud agnostic and customizable orchestration of applications. Now, how MiCADO does this, we can talk about it on the next slide. Now, so let's assume that the application developers put all these various aspects which we discussed in the last slide. For example, the resource specification, the service description, and the mapping and the various policies required for the application's management at runtime. The application developer has to put this into a configuration, which in the context of MiCADO, we call it MiCADO-edge or application description template file. And this application description template must be in a specific format, which is a YAML based format, but it is in the following the standard specifications of Tosca. Now, Tosca is a standard modeling language to describe the topology of cloud-based services, their components, relationships, and the processes that manage them. So this Tosca-based ADT files will be submitted to the MiCADO systems. The MiCADO system translates these ADT files, and then based on the resource specifications, it will dynamically create the virtual machines, which is being done by the MiCADO master, which is a component of MiCADO, which I will further explain on the next slide. So MiCADO master will create these virtual machines, and once the required virtual machines are created, then the services will be deployed as per the service to resource mapping performed in the description accordingly. And once the deployment has been completed, then MiCADO masters will start managing the runtime executions of this application as per the defined policies, scaling and monitoring policies defined in the description file. Now, what is this? What is it in this particular box of MiCADO master and the workers? We will see this on the next slide. So, if you focus on the from the left side, you see this application description template, which is the description. This will become an input to the MiCADO system and will be provided to MiCADO master node. Now, MiCADO master node is basically a virtual machine which will run these component of MiCADO system. We call it MiCADO master node. Now, on this MiCADO master node, if you see, there are like a set of components. Now, if you see, they are divided into two different rows. The first row, which contains submitter, policy keeper, and optimizer. The second is the cloud orchestrator, container orchestrator, and monitoring system. So the first row, if you notice, these are the components which were specifically designed for MiCADO systems. So these are like self-developed components, where the second row consists of various already available open source solutions which we integrated into MiCADO system. For example, in the cloud orchestrator, we have Octopus, an open source tool, and Terraform. Now, these are two different cloud orchestrator tools which we integrated. And the job of the cloud orchestrator tool is to dynamically create and delete the virtual machines whenever it's been needed. For container orchestrations, we integrated Swarm initially, and then later on we also integrate the Kubernetes. And for monitoring of the resources and applications, we use this Prometheus tools, which is a very popular tool for monitoring systems. So we integrated it into MiCADO system. Now, in the upper row, we have the submitter, whose purpose is to translate the input file submitted to MiCADO system. The policy keepers, which enforce at runtime, which enforce the scaling as per the description provided by the users. And an optimizer component, which is a machine learning based optimization components, whose job is to recommend the scaling actions, and once it's recommended, then the policy keeper then execute those scaling actions. On the other side, we have the MiCADO worker node. So this consists of the monitoring agents, for example, consists of CA advisor and node exporters, which, if the user specified that the monitoring needs to be performed for a particular services which is run on a specific worker node, then this can be deployed on those specific worker nodes, and at run times they will monitor the various metrics related to the resources as well as the application, and these metrics will be pushed to the MiCADO masters, and MiCADO masters will utilize these metrics at runtime in order to make the runtime scaling decisions. Now, the key important thing was the input, the application description template provided by the users to MiCADO systems. So if you look into it, we earlier said in the very first slide, in the context slide, that this consists of all the various descriptions required for the application. For example, it will consist of the cloud infrastructure details, like what kind of worker nodes will be required, what are their details. For example, in this case, if you see, so this is the definition, a sample definitions for a worker node. In this case, it belongs, it defining a Cloud Sigma worker node. Cloud Sigma is a European cloud providers. And then it also consists of all the various details. For example, what would be the instance size, the SSH keys, the ports, and the VM image, those details. But it also, on the other side, you will see an example of the service definition, the container-based service definition. For example, the name will be stress-ng, for example, and it is a Docker deployment-based service, and then the image of the service, the various required details like the arguments and the resources, all can be configured at the description stage. Now, further on that, the important aspect is the two key things, which is the monitoring policies, like the monitoring subsystems, and the other key important feature is the customizable scaling systems provided by MiCADO system. So if you see, for the monitoring system, so the users will have the facility to kind of turn on and off the container metrics and the worker metrics, the node metrics, from the descriptions. If it is needed, they will turn it on. If it doesn't need it, it can be turned off. On the scaling side, MiCADO supports both container level scaling as well as the virtual machine level scaling. And the other important thing is that users will be able to provide their own programmable based scaling logic, and this programmable scale logic will be based on Python. So users will provide their own customized small programs which will dictate the logic behind the scalings, which will be then adopted by a MiCADO system and ensure at runtime. So what does this facilitate the users to facilitate them and enable them to come up with various kind of strategies for their scaling. For example, they can perform scaling based on the load, the utilization based, the deadline based, event based, schedules, and depends on the user's requirement. They can come up with any scaling logic which will then be ensured by MiCADO system. And as I mentioned, that it can be both for containers. For example, in this case, we can associate a scaling policy for a specific container. For example, in this case, stress-ng, which we already specified in the previous slide as an example of the container specification. And also in this case, for example, we can associate it with a particular virtual machine node type, and then the scaling policy will be dictate the behaviors for those particular virtual machines. Now, as an example of what kind of policies and what would be this customizable programmable based scaling logic, we can see an examples here. So, for example, on this side we have for the container, and on this side we have for the virtual machines. So it is a lot of code here, but I would like to just kind of point out on the various bits and pieces. For example, what we can do is that based on the monitoring metrics, we can associate alerts, like where we can say, oh, service overloaded based on certain specific Prometheus-based matrices. For example, in this case, container CPU usage, seconds totals. So we can associate a role which will determine the behavior of service overloaded. And then here on the scaling rules, so if you see, this is a Python-based custom code provided by the users, so they can implement any behavior as a result of any alerts generated, customizable alerts which they programs and associated with that policy. And the same things here in the case of the virtual machine policy. So in this case, this policy will dictate the behaviors of a specific virtual machine type. And in the same way, here we can also associate and make rule-based alerts based on the Prometheus-based monitoring metrics, and then provide a scaling logic in order to determine what shall we do in response when those alerts are being generated. Okay, so that was the general MiCADO system, very quick and brief overview of MiCADO system and how it works. Now, if we look into one of the extensions, which was JQuery based extensions, so in order to understand the context of this extension, so consider we have this batch application. So the batch applications consist of multi-job experiments, where sometimes it happens that we have the need that we would like to complete all the jobs of the experiment by a certain specific deadline. So what we need is that for a specific experiment, we would like to associate it with a deadline, and we want that all jobs should be completed by that deadline. But what is the problem is that because each job of the experiment could be of stochastic nature, so we cannot determine the exact durations of the whole experiment based on the number of jobs. So now the question arises that, okay, how to dynamically deploy and execute the worker containers which will run the specific jobs in the cloud environment, and how to gather monitoring statistics so that we can determine at runtime by when the experiment could possibly be completed, and then how to ensure that we can complete the experiments with all the jobs to be fully executed by a specific deadline. So in order to achieve all these various tasks mentioned here, what we did is that we extended MiCADO. We come up with another utility called JQuery, and then we integrate it with MiCADO so that we can achieve the behavior of deadline-based execution for batch-based application. So what in this case, what we do is that we develop this tool called JQuery, which is a cloud-agnostic asynchronous distributed task queue, and this component consists of tool consists of two key components. One is called manager, and the other is called agent. The purpose of the manager is it mimics the behaviors of job queue, and the second is that it monitors the executions of jobs which are part of an experiment. And the agent components run on each worker node, and then what it does is that it fetch and executes the fetch jobs from the queue and then execute it on the worker machine. So now this JQuery is a asynchronous distributed task queue. When it's integrated with MiCADO, what we did is, which is a cloud orchestrator, as we earlier explained, the MiCADO responsibility is to gather monitoring statistics from the JQuery manager component, and then calculate a scaling policy and calculate a number of virtual machines that is at any point in time can be measured as per a deadline provided deadline-based scaling policy in order to calculate how many virtual machines will be required, such that the executions of all experiments will be completed as per the deadline. Now, in order to understand how this works, I provided this diagram just to give you a brief overview of how these two tools can work in integration in order to achieve the deadline-based policy behavior. Now, consider here, for example, we have an experiment. This experiment consists of, let's say, multiple jobs. In this case, for example, 200 jobs, and the deadline for this experiment is to be completed within 1 hour. Now we have this, the user has to specify these jobs definitions in a file which would be of JSON type. For example, here we specified this specified the job definitions, the technical job definitions, like what kind of inputs data, what kind of output data it will produce, what would be the arguments, and all those various details which I did not provide it here. That could be depend on the nature of the jobs. But other than that, what it will have is that the experiment will have a deadline, like, in how much time this experiment should be completed, and in initial average estimated time for one task or one job. So just this experiment will be provided to the JQuery manager component, and with JQuery managers will be run in itself by MiCADO masters. And once MiCADO master receive this experiment file, and based on the deadlines, and initially based on the estimated job duration time, it will calculate based on a user provided deadline policy. It will determine how many virtual machines or worker nodes at any point in time will be required, such that the experiment should be completed within the specified duration, for example, in this case 1 hour. So initially it formulates these number of worker nodes based on the provided estimated duration. However, in runtime, once the first job start completing, and as and after that, once the job start completing, it will determine the actual time based on their average job execution time in order to change these number of worker nodes accordingly, such that the overall experiment should be completed nearer this specific deadline. And this is how it works. Now, the second extension, which was the MiCADO-edge, which is in a simplistic terms, which is handles the containers executions in the extended cloud to edge ecosystem. Now, in order to understand the overall context, so we already spoke about the MiCADO system. So if you see, this diagram represents the conventional cloud to edge ecosystem, where usually there are cloud layers, then there is possibly a fog layer, and then an edge layer. So, and maybe one or more than one fog layer in between. So now if you see there, so what we did is that we kind of generalize it into a cloud layer and a non-cloud layer. So now for the cloud layers, we already have this MiCADO system which manage the deployment and runtime execution of the containers in the cloud environment. However, there is these IoT systems which also simultaneously need resources from the cloud as well as from the non-cloud layer as well. So what we needed was to extend MiCADO capability such that it handled the multi-level orchestration for the cloud to edge ecosystem. Now, in order to extend these capabilities, what we did was that we integrated another open source tool called JQuery Extension, which is an additional tool that assists us from bringing MiCADO functionality from cloud only to also capture the cloud to edge ecosystem as well. Now, how we did this? This is the architecture diagram for MiCADO-edge, which also integrates these various components of the JQuery tools, which we mentioned earlier. So now, if you see on the cloud layer, this was exactly like the previously described MiCADO system, where the system will accept a Tosca-ADT file, which will describe the various details related to the application and resources and all those things. It will be provided to MiCADO master. MiCADO master has these various components which we earlier specified, and also Kubernetes for the container orchestrations. But it also have now one more component which is called Cloud Cores, which is a component from the JQuery system. JQuery in itself is an extended utility which extends Kubernetes behaviors from cloud to cloud edge. And that's why we integrated it, because a MiCADO system is based on this Kubernetes system. So it was a natural fit for us to integrate it so that we can extend the cloud orchestration system to also include cloud to edge orchestration as well. So now Cloud Core, now we extended MiCADO master by integrating this additional Cloud Core component. On the cloud worker side, there is nothing changes. However, what we did is that for the non-cloud resources, for example, either in the cloud fog edge scenario or directly cloud edge scenario, what we did was that for each worker node, for each physical resource outside the cloud domain, we added this additional agent, the JQuery agent called Edge Core, which is also another component of JQuery Edge. And what this does is happen that the communication between Cloud Core and Edge Core component enable us in order to achieve this orchestration behaviors of Docker containers and non-cloud resources as well. And once we integrated that, then the rest of the system behavior is exactly the same as we previously described for MiCADO worker node. So the only difference is that the cloud workers are running without Edge Core, where the non-cloud workers, for example, this one and this one, these are all running with the Edge Core component. Now, for us, the advantage was that now with the single description file, Now with a single uniform descriptor ADT, we can describe the entire cloud to edge applications can be easily described without having any kind of distinctions making between the cloud resources versus the edge resources. So for example, now in order to see an example of such an ADT, so consider this, for example, in this case, we are defining an edge node in the ADT. So for example, the name of the edge node, edge worker node, and we specified this custom Tosca type for this, like edge. So this will determine that this resource is an edge resource, and then we can associate additional properties with this. For example, in this case, the public IP of the non-cloud resource. Now, on the service definition, so now, for example, in the service mapping, so if a users want that certain services of an application need to be hosted by edge resources rather than cloud resources, so what will happen is that we can define the service as the normal service, like in this case, the Docker service, the image and various details of that service image. But then in the requirement, we can just simply specify where it shall be hosted, and in this case it will say host by Fog Edge, and Fog Edge in our description in this case would be an edge node, and in this way we can have the uniform description for the application irrespective of cloud or cloud to edge environment. And this thing not only limited with respect to the resource and service description, but also at the scaling policy level as well. So now, for example, in the previous slide, as you see, we define a service, for example, FD processor in this case, which would be hosted on an edge node, and then we can just attach as whatever scaling policy we would like to attach with this service. We just specified that, okay, the policy needs to be applied on this service like here, and then we can define a scaling policy, a custom scaling policy for that service, and then MiCADO will ensure enforce this particular scaling policies at runtime without making any distinction whether this policy is associated with a resource at the cloud layer or in a resource with the on the edge layer. Okay, and that's almost the end of our presentation. So in summary, MiCADO is a cloud agnostic orchestration solution. Its architecture is completely pluggable, where it consists of all components of this architecture is completely open source. And is pluggable in the sense that one component can be replaced with any alternative. For example, we use different kind of cloud orchestrators, we use different container orchestrators, and we can just kind of switch between them with just a single configuration. And interestingly, MiCADO is based on the standardized Tosca-based application and policy descriptions, which facilitate this interoperability and agnostic behaviors across different cloud environments. MiCADO facilitates automated application deployment in cloud, and it facilitates application owners with highly customizable scaling policies where they can come up with their own scaling logic and develop providers policy which will dictate the behavior of their application at runtime. And lastly, it supports a large variety of cloud providers. For example, the current support is for Amazon, Google Cloud, Oracle, OpenStack-based private clouds, Microsoft Azure, and some European providers, for example, EGI, Cloud Broker, and Cloud Sigma as well. Thank you very much.